start. It's been a really long time since we had I actually don't remember any nuclear physics colloquium, but it turns out that the field is alive and kicking with new excitement and new results. And Nir Barnea will give us a little bit of overview and a little bit of his own research on the field. And I hope it will stir some interest. Nir, please.
So thank you. Do you hear me well? No. Okay. So good afternoon, and thank you very much for the invitation. I'm really excited to be here. First of all, to give this historic colloquium, first reason, and second, since my son is a student here, so it's a real pleasure. I will try in 45 minutes, 2 hours, how much? 50 minutes. To tell you something about nuclear physics, what we are doing today, and what we find interesting and exciting. I hope that you will find it as interesting, as exciting as we find it. But okay, let's see. I will try to cover many things, but briefly. So let's start with some preliminaries, some nuclear trivia. These slides encapsulate more or less all you need to know in the graduate level post-nuclear physics. So there are neutrons and protons. They bind to make nuclei. This is the nuclear charge. Here are the number of neutrons, number of protons. Roughly, when you look at the light nuclei, number of protons, number of neutrons is equal. When you go to the heavier nuclei, there is neutron access to the Coulombic propulsion. So around here, you have something like 50% more neutrons than protons. Then, when you try to understand what's going on in the nucleus, you realize that to a large extent, the nucleons, protons and neutrons, behave very much like rigid balls. That means that the volume of the nucleus is roughly proportional to the number of the nucleons, A, therefore this relation for the radius, and the density is almost a constant. Then, if you want to understand the systematic of this math, you have this very nice equation. It's called the mass formula. Don't take it too seriously. The one thing that I want you to remember from that is this symmetry energy. This tells you what will be the effect of enlarging the number of neutrons in a nucleus. Okay? And we just need to know that. You need to know this symbol, asymmetry, that tells you what happens when you increase the number of neutrons or the number of protons. So this was graduate level course in nuclear physics, crash course. Then let's go to the topic of my talk, which is the size of the nucleus. So actually, this question is not completely well defined, because we have to ask ourselves, what size are we discussing? It could be like a picture of here, the charge radius or proton distribution, which would be just that line. It could be a neutron distribution. It could be the matter radius, which is just the average between these two. Or it can be another quantity, which is the weak charge. Maybe you have noticed that, maybe not. But whereas when you look at the electric part of the world, the charge of the neutrons is 0 and the protons is 1. When you look at the weak interaction, the situation is almost reversed. The charge of the neutron is almost -1, and the charge of the proton is almost 0. So if instead of measuring charge distribution, you will be able to measure weak charge distribution, you will actually measure the neutron distribution. Then there is another reason why this question, what is the size of the nucleus, is not a well-defined question. And this is because only quantities that are associated with some current can be measured. Others are not protected under unitary transformation. Therefore, they are not measurable. For example, neutron radius is not well-defined quantity. Nonetheless, I'm going to discuss it almost all this talk. But to be fair, let's assume that this is what I mean. Okay? It is the charge, weak charge radius that I'm looking at. Anyway, over the years, people dedicated a lot of effort to try and measure the size of the nucleus, of nuclei. Of course, everybody learned about the Rutherford experiment many, many years ago. And indeed, if you consider the charge radius, which is roughly the distribution of the protons in the nucleus, this is a well-measured quantity. You can measure it with electrons, like Rutherford did, with muons, with any charged particles that you want, and you get a very nice and solid result. However, when you consider the Newton distribution, the situation is very different. People try to measure it with many, many probes. However, most of them suffer from a big drawback. And that is, they interact strongly with the nucleus. Therefore, they are all model dependent, and there is a question whether what we think we are measuring is actually what we measure. And this is true for these antiprotonic atoms, pionic atoms, proton scattering, etc., etc., etc. The most promising approach to really measure the Newton distribution in a nucleus and do it in an unambiguous way is just to measure the parity violation or the weak charge of the nucleus. And indeed, parity violated electron scattering is what is people trying to do today in order to pinpoint the size of the nucleus. And in the next few slides, I'm going to discuss these experiments. So, as crazy as it sounds, and you can immediately realize that it will be a very, very difficult experiment, people try to measure, really measure, the weak charge or weak distribution of the nucleus. The idea is very simple. Of course, the application or taking out that this experiment is much more difficult. The idea is that if you have a left helicity or right helicity electron, their interaction with the weak charge is different. So you take a beam of left polarized electron, then a beam of right polarized electron, measure the cross section, and take the difference. So this is what is written here. And from that, you can get the ratio between the weak form factor and the charge form factor. And from the weak form factor, if you make a small q expansion, you can in principle get the Newton radius or the weak radius of the charge. This is an experiment that was done in JLab. It was called P-Rex because it was done on lead. So this is lead is TB, so it's a radius experiment. And this is the result. What they have done here is just they measured this parity violation asymmetry, and from that, using this mean field model, try to extract the radius. So this was the first experiment of this kind. In order to get the full form factor, it would probably take a decade, or few decades even, because each point is really a pain to measure. But now we are planning a new experiment on calcium, and the reason for that I will postpone for later. But this is one approach that is now being pushed, very challenging, but very clean. Another approach is to use the electric polarizability or dipole polarizability of the nucleus as a measure for the radius. So, first of all, what is electric polarizability? Formally, this is this expression, so this is integration over the response function divided by the energy of the photon. In principle, what you should look at is this diagram. You have to consider a system where a photon comes in, you have to consider all possible excitations, and then the photon goes out. So this is in principle what is encapsulated in this expression. And now you have to ask yourself, okay, what is the relation between this polarizability and the radius? So the idea, roughly speaking, is the following. If the same system is larger, is to some extent less rigid. Less rigid means that it will be easier to excite. If it is more tightly bound, more tight, then it will be more difficult to excite. Therefore, you would expect some correlations between the electrical polarizability and the radius. And this is what you see in this graph. You see that for many mean field models, there is a very strong correlation between, this is now the skin radius, which is just the difference between the radius of the neutrons and the radius of the protons, and the polarizability. There is another factor J, which is roughly this symmetry energy that is well known. So another way to measure, okay, this now is really measure, not really measure, the radius is just to take this experiment, measure this quantity, the polarizability, and then use this kind of graph and deduce the radius. So this is another approach that actually there is a laboratory in Japan, CNP, that carry out such experiments. Now I would like to relate this measurement to very different world, and that is the nuclear equation of state. You may ask yourself, what is the relation between the radius of this tiny object, the nucleus, and the equation of state which impact the structure of neutron stars? That's a good question. Bear with me for this slide. So it's convenient to write the equation of state instead of neutron density and proton density as a function of the nuclear density rho and the difference between the neutrons and the protons. And then you can write the equation of state as a function of the density and corrections to this asymmetry between the number of neutrons and the number of protons. Of course, what we are interested in order to study neutron stars is of course a situation where all of them, nucleons, are neutrons. That is delta equal to 1. What we can measure in finite nuclei is of course situation where delta is roughly equal to 0. So that's definitely not equal to 1. So in order to proceed, we expand this factor S of rho and write as J times L times X. So X tells you how far you are from the normal nuclear density. And then you realize that this quantity we already know. This comes in the mass formula, it is well established, very accurately. However, this other factor that controls the Newton equation of state is not known at all, because we don't have any natural way where to measure it. There are no bound Newton systems. We cannot make a box full of Newtons and compress it to measure the equation of state. So the question is, how can we tell empirically, not theoretically, what is the value of this quantity, of this L? So the Kurzman answer is the following. Now you may laugh. But this is the best we can do in order to tell what empirically, what is the value of this slope parameter. The only low density Newton system that we know is the skin of finite nuclei. So this is a real thermodynamic system, it may be 50 particles, but this is as best as we can do empirically. So the idea is to try and relate the radius of the nucleus, or the skin radius, to the equation of state of nuclear and neutron metal. And from that, tell something about the structure of neutron stars. This is the program. And interestingly enough, if you consider many mean field approximations, or mean field models or theories, you realize that there is a very strong correlation between this parameter L and the skin radius. Here specifically, we are discussing the skin radius of lead 208. So now, the only thing you should do is just measure the skin radius, and if you do this, we can deduce the value of this L parameter. And this is what was done. And here you can see output of 3 different measurements. One is P-rec experiment of parity violation. This is this blue huge error bars. Then there is this smaller error bar from proton and lattice factoring, which is better. And then there is the best, most accurate values coming from dipolarizability of the nucleus. And this is the smallest measurements. And using them, one can deduce that the value of L is just 46 plus minus something MeV. So this is a way that you can relate measurement of the nuclear size to the nuclear equation of state, and from that, in principle, can calculate the structure of neutron stars. The caveat in all these nice correlations is that they are all based on mean-field models. That is, people come out with some ideas how the nuclear effective potential should look like, fit to many data points, and then try to predict some other things. As long as you are within the neighborhood of what you fitted, of course this should work very nicely. However, when you try to go a bit further, it might be correct, it might not be correct, but since this is not really based on some more fundamental theory, you don't know what is the quality of these predictions. A better approach would have been to start from some Hamiltonian that is based on, let's say, QCD, solve it for lead 208, see that you predict the spin radius in accordance with what is measured, and then go and calculate neutron matter and see what you get. So in principle, this is what we call the ab initio approach to nuclear physics. There are only 2 problems in this approach. One is that we are unable to solve QCD, at least not in low energies. Therefore, we cannot deduce the nuclear Hamiltonian directly from QCD. The second problem is that given that we have a Hamiltonian, to solve the structure of finite nuclei with, let's say, 60 nucleons, this is a rather complicated problem because there is strong correlation between the nucleons. They don't give up easily to a mean-field approximation. So also to solve the many-body problem, it is an hard stuff. So this is the situation regarding this ab initio program about a decade ago, 2007. And you can see that here in red, this is the range of nuclei that people were able to calculate directly from some given Hamiltonian back then. In the last decade, however, there is a huge jump in the number of systems and in the quality of what can be done ab initio. That is, to start with a given, well, almost honest to God Hamiltonian, and go and solve the many-body problem. And in the rest of this talk, I will try to show you what are the lines under which this program is carried out, what is the connection with QCD, and some of the highlights of what we are able to achieve. So let's start with Colloquium 48. Why is Colloquium 48 so important? It is important because it is really at the tip here of what we can do. So this would be a very natural meeting point between ab initio methods and these mean-field approximations that all these nice correlations that I presented a few slides ago were based upon. Then there is another aspect to Colloquium 48 that is important. Most light nuclei have equal number of protons and neutrons. Colloquium 48 have 20 protons but 28 neutrons. Therefore, this is relatively neutron-rich nucleus. Therefore, we can use it to test some of these questions about the difference between neutron radius and proton radius. So what you see here is, in essence, comparison between ab initio calculations of calcium-48 and mean field calculation of the same nucleus. Here, the diamonds are these mean field calculations. Squares, these are not experimental data. This is just different calculations. They are all done in the same calculational method, but the input Hamiltonian is different. Actually, it's not the Hamiltonian that is different. It's the same Hamiltonian, but the parameters that control the Hamiltonian were fitted in a different way. And what you can see is that if, for example, we consider here the neutron radius, there is a very strong correlation that all these calculations are in line. And the same goes with the electric polarizability. So comparing these two figures, we can see that also in this ab initio calculation, we find this nice correlation between neutron radius and the polarizability. Then we can also look at the skin radius. The problem is that predicting these quantities, you really need to do some kind of fine-tuning of your Hamiltonian. And you see that most of these ab initio calculations do not really fall in line with the measured proton radius, which is this green line. So the way that we proceed in order to make predictions for unknown quantities is to use some empirical data. In this case, is just the proton radius, and deduce from that a prediction for the neutron radius. This is what you see here for the proton radius, for the neutron radius, for the polarizability, and for the skin radius. And you can see that whereas for polarizability and neutron radius, there is a nice agreement with these mean field theories. When it goes to the skin radius, there is a huge difference. Our ab initio prediction is much narrower and much smaller than what these theories predict. Now we can, yes?
Can you please explain what we see in the y-axis?
What here?
Yeah, what is it?
This is the measured proton radius. This is the charge radius of the nucleus. Okay? This is what you get when you scatter electrons from the nucleus. Okay? So now we can make check this prediction. And here you see a comparison between our theory, which is this blue, and different extractions of this neutron scheme. And you see that this prediction works rather nicely. So this is a nice success to this ab initio methods. Then we can make some other predictions. For example, the forthcoming Search experiment, which will calculate, which will measure the weak form factor of this nucleus, is planned to be in momentum transfer of 0.8 inverse Fermi. So this is our prediction to the weak form factor. We'll see in a few years whether we manage to pinpoint this quantity or not. Then, regarding the nuclear equation of state, the same technique, we can now extract the value of L using, again, the proton radius and our values for calculating L. And then we can see if we compare the value that was extracted from the electric polarizability with our prediction, we see that there is a very nice agreement between these two numbers. So our prediction for the nuclear equation of state is consistent to what is being done from the combination of electric polarizability of the system and these mean field theories. So this is to some extent reassuring, but this is to some extent only the beginning. So now let me take you through the full program of nuclear physics this day. So the idea is to start somehow from QCD, then write down potential, currents, solve Schrödinger equation or whatever equation that you would like, and get to observables. So old school looked very much like that. There was no relation to QCD, and people will come out with a potential based on Yukawa theory of pion exchange, feed them to experiment, and make predictions. This was a very successful program, really very successful. If you look now at the comparison between theory and experiment for all the light nuclei, you see that if you include 2-body and 3-body forces, you have very nice agreement for many states. Really successful. That's successful, but I think there is also a stamp with for this NN potential.
What is theory and what is experiment? How do I know that it's successful?
I'm telling you that you should believe it. But if this is not enough, you see this green, maybe this map is not very clear. This is calculation done only with 2-body forces. This is 2-body plus 3-body forces, and this is the experiment. So for example, you see with helium-4 that 2-body force is not enough to match experiment, but you can use add the 3-body force, you have very nice agreement. Same for lithium-6, lithium-7. Okay, lithium-8 agreement is not maybe that nice. Lithium-8 is very nice. Lithium-7, very nice agreement. Even for carbon, this agreement is not that bad. So, very nice reproduction of the data. And most of the parameter potential were fitted in the 2-body problem. Maybe 3 or 4 more parameters were fitted to some of these things.
So how many parameters are there?
Overall, I think some order of 35. But most of them are very real in the 2-body system. So there's a lot of effort fitting the 2-body scattering, which is taking something like 30 of these parameters, and then you have something like 3 or 4 more free parameters to fit the 3-body force. And this is usually fitted in the 3-body system, and maybe of course on lithium-6. And all the rest is predictions. Yes?
You said lithium-8 is not as successful?
Look, that?
Did you say lithium-8 is not as successful with 3-body? Lithium-8 is not as successful with
Lithium-8, well, it is successful, but okay, it's not really I did experimental error.
It has a halo neutral instead of this.
It is halo, yes. But also helium-6, it's not shown here. Is halo and it is produced rather nicely. Okay? So this is the old way of doing things, but successful. From the 90s on, field of theoretical nuclear physics went really a fundamental revolution, rewriting everything that we knew from scratch. And this revolution is still in progress. This is not done yet. And the idea is to really try to make this bridge between QCD and nuclear physics in a more fundamental way. And the starting point is the following observation, that if you look at QCD, you would realize that the mass of the light quarks is much smaller than the relevant scale of QCD, which is roughly 1 GeV, the mass of the neutron and the proton. On the other hand, you see that these quarks are roughly of the same mass, roughly 0. Therefore, you have some symmetry in the problem. This is the flavor symmetry of isospin, which is just rotating these up and down quarks, one between each other. When you ignore or neglect this mass of the quarks completely, just put it to 0, you realize that this symmetry, this isospin symmetry, is extended to left SU2 symmetry and right SU2 symmetry, because left and right quarks become independent of each other. The only thing that couples them is this mass term here. So if you remove it, then you have this higher symmetry. This symmetry is, of course, not realized in nature. In nature, we don't see it. So we assume that it is spontaneously broken into some other symmetry, which is just this isospin symmetry. And of course, when you have spontaneously broken symmetry, you also expect to get some Wilson bosons. And there are also natural candidates for being these particles. And these are the pions, since the mass of the pion is much, much smaller than the mass of the neutron or the proton. Much, much smaller is not 3 orders of magnitude, but it's almost 1 order of magnitude. This is what we can do in nuclear physics. So the new theory of nuclear physics is essentially developed along these lines. That is, we look at neutrons, protons, and pions as particles that manifest this broken chiral symmetry. I don't want to go into the algebra, it's very nice mathematical theory. And then you write an effective field theory, starting from this chiral Lagrangian, and adding term order by order terms that are essentially an expansion either in the edge between the pion mass and the nucleon mass, or typical momentum and the nucleon mass. Both these ratios should be of the order of 1/10. So we would expect this series to converge rather fast. Unfortunately, this is not exactly the case. In this approach, we have now a full theory. We know how to relate QCD and produce an effective Lagrangian. From that, we can deduce potential and currents, and have a full and complete theory, which we can improve order by order by order until we can describe everything that we want. Sounds simple? It isn't. In principle, this is the way the nuclear force look like in this program. These are the orders, and then we have 2-body force, 3-body force, 4-body force. The first success of this theory was the identification that 3-body force should be there, and what should be the relative strength. And you see it appears here. This is order Q3, Q cubed, and this is roughly what we expect. And this comes naturally. It's not, it was a big surprise early on when people realized that 3-body forces must be there. Now you realize that it must be there because it just appeared. Now in this picture, these lines, this is pion exchange between nucleons. Dots are contact interactions. So for example, in leading order, which is that, you have 1 pion exchange, and then you have 2 short-range interactions, which can be essentially described as delta functions, the interaction between the particles. So here we have 2 free parameters, just this one and this one. You go to next order, we have another 7 parameters. Next order, you have no free parameters at the 2-body level, but you have 2 free parameters at the 3-body level, etc., etc., etc. And all these parameters should be fitted to experiment in order to reproduce the data. So this is the program. If we really need this 4-body force in order to reproduce data, we are in big trouble. This is almost undoable computationally. Anyway, once we have the potential, we are left with a simple problem, which is solving the many-body problem. I will not discuss too much about that. There are many, maybe 3 methods that now able to tackle this problem in a reasonable way. Different implementations, order for accuracy, essentially the same. Some of them are better, some of them are worse. I will just represent in 2 slides one of this method, which is a coupled cluster. This is a theory that was originally developed in nuclear physics, maybe in the 70s, maybe earlier, then neglected for many decades, taken over by chemists, developed to full, and then brought back to nuclear physics, and now it is rather successful. The idea is that you start with a single stator determinant. It must be a closed shell, otherwise it's not doesn't work properly, and then you take into account one particle, one whole excitation, two particles, one excitation, etc. Put them into an exponent and get a very reasonable approximation for your wave function. This is the approach. You can be even very smart and draw some diagrams. The essential thing is that with available computational resources, we are able to do one particle, one all, two particles, two all. This can be done. It is to include three particles, three all. This becomes difficult, doable, but that's it. We cannot go beyond that. It's become way too expensive from computational point of view. So this is where we stop. And so for some quantities, you can get an accuracy of a few percent. For some other quantities, okay, relative quantities, you may go to the sub-percent level. A more difficult problem is not calculating ground state properties, but actually calculating reactions. The problem with reaction is that, in principle, when you calculate ground state, you have the variation of principal at your A, and things are relatively under control. But when you want to calculate reaction of, let's say, 12-particle system, and you want to do it over all energy range, then you need to take into account all possible excitations of the system. Well, if you have elastic scattering, nothing happens. Then you may excite it to some bound excited states. That's reasonable. Then you may kick out one particle. Then you may kick out two particles. Then you kick out four particles, and they will form a new particle. And all these things need to be taken into account. So this is really a mess. The question is, how are we going to do that? So, in order to calculate the polarizability, for example, this is exactly what is needed. Let me just comment that solving this final state wave function in full, taking into account all possible partitions and breakings, is done so far only up to 4 particles in nuclear physics. This is as far as this went. So if you want to calculate reactions really in full, we should come out with a smarter approach. So question is, do we have a smarter approach to do that? And the short answer is yes, and I will spare you the details. But I will just outline the solution. The idea is that instead of calculating this response function, where you explicitly need all these partitions, all these complicated final states, we can look at some transform of this quantity. This is transformed with the Lorentzian kernel. If you do that, then you can write this quantity just as some, maybe very complicated, but it is a ground state expectation value. This can be calculated. Actually, this boils down to solving Schrödinger equation with a source. So this we can calculate, then we invert this transformation, and we can get this response. So this was done, even for larger systems. Now we are doing 20 particles and even more. But I would like to demonstrate it on the polarizability of oxygen-16 and calcium-40. Just to demonstrate, in this case, two things. First, the correlation between the charge radius and the polarizability that we have seen in mean field theories, but not as much in ab initio calculations. So here you see that there is really strong correlation, and these are different parameterizations of this EFT Lagrangian. And you see that only when we add three body forces, we manage to reconcile theory and experiment. So this is, again, the demonstration for the importance of the three body force in nuclear physics. Then we can be bold and make predictions to even larger systems. And this is really the limit where we can get these days. So maybe in a decade or maybe 5 years, maybe next year, you'll be able also to make predictions for lead flow rate. And these are predictions for what people are going to measure, and with that we can again do this exercise and see what are our predictions for the nuclear equation state. So with that, let me finish this talk.